So homework has only got 4 problems in it, so how hard could it possibly be? I mean, really, there's only 4 problems.
Right there.
Okay, let me guide you through this very quickly. Here, in problem number 1, I'm having you generate the 5th Hermite polynomial, and this follows page 7 of the notes. In page 7, I took H2 and H3 and generated H4. I'm having you take H3 and H4 and generate H5. So so it follows that exactly what I've done there. Just verify that it produces the 5th Hermite polynomial, which I have the answer right here on page 7. So you already know if you've got it right. So there, you should generate that polynomial. So you'll build that up there, you'll build a wave function, and then in part C, just simply show that it is normalized. So use then the normalization constant provided here. So there's your normalization constant, build the wave function, integrate it. Remember, it is symmetrical integral, so make use of that. So there's your normalization constant, just generate that, it integrates to 1. Your integration limits, of course, are minus infinity to infinity on that. All right, and then H2, we'll get to that one in just a second. I'm going to get down, we're almost done here. And then we have all our motions taken care of. Remember that we've got translational motions in very, very high quantum states. We have rotational motions, which are intermediate, which get better with the weight. And then we have vibrational, and 2 of our concerns in vibration were, if the amplitude is too big, then we have this graphic. Where is it? Come up here. We have this graphic here. If the amplitude of the vibration is too large, we get up into this region, we're going to have a lot of error. But if it's small enough, we're down here, we can get away with using a harmonic model. Well, good news was that for under thermal conditions, the vibrational quantum state is at 0. N equals 0 is allowed for the vibrational system because it has a 0-point energy. But we find out that for our vibrational system, we're down here, which is very good news, because it solves 2 problems. It solves the problem of error of being up here, and it also solves the vibrational rotational coupling problem. Is that if the vibration is very broad, then it will couple with the rotation very, very badly. But being that it's in very, very low quantum states, and we get a value, when we did it at thermal, at KT, we got an average quantum number almost 0, which is exactly what we want. In here, I added this just recently. This isn't in your current notes, but the masses and reduced mass that I had was for HCl, and we had the ratio of the root mean square, how far it expands when it vibrates, the bond ratio. So it had something along the lines of about I think I got that quite right here. In the ground state, let me move this up a little more further. We had a fairly small number. Bring these up here. So we got something at just a little bit less than 6%. What I did in here, I added the masses to make it chlorine, Cl2. And so for the heavier masses, that 6% dropped down to something a little bit less than 4. So what it's saying is what we saw in our rotation and the correspondence principle. As the masses get heavier, then our assumptions actually do get better, which is really good. So I did it for chlorine, and we found out that the range of the moment of inertia is only about 7%. So the heavier the molecule is, the more fine-tuned the vibration is. And then where we left off is that we had our average quantum number still somewhere around 0. Is we've got this then, take it back up here. Here's our harmonic oscillator. It says that it spends most of its time at its equilibrium distance and over in here. The question we want to ask is, what is the probability that the vibrational system extends beyond what is classically allowed? Well, the maximum energy, our energy of our quantum system was n plus 1/2 h nu 0. Nu 0 is 1 over 2 pi root k over mu. So this becomes n plus 1/2 Planck's constant over 2 pi root k over the reduced mass mu. Now, when the classical particle reaches its maximum turning point, then it is at its maximum amplitude. All the motion is, there's no more kinetic energy, it's all potential energy. So classically, this becomes then 1/2 k the amplitude squared. So there's no kinetic energy, it's all potential energy, it's stretched to its maximum ability. It is now momentarily at rest. So that is its amplitude. So this then becomes n plus 1/2 h bar root k over mu. So the amplitude, if we use this, becomes 2n plus 1. If I take the 2 across, then we have then 1 over the square root of k mu, or h bar rather, h bar over the square root of k mu. This is 1 over alpha as it was originally defined in the wave function. So you end up, the amplitude is 2n plus 1 over alpha. Is what you get as a result of the square root of that. So what I want to ask is, what is the probability of finding a vibrational particle that extends beyond what is classically allowed? That's a quantum tunneling effect. So to do that, what we will do, we will take an integral from the amplitude to infinity, where this is the classical version of psi star psi dx. And because we're going to take in 2 accounts, one is the stretching, but remember there's 2 turning points. There's an outer turning point and an inner turning point. So I'm going to double this and make that 2. So we'll do this for the n equals 0 ground state to see what that is. So I need the ground state wave function. So here is this is our classical amplitude, 2n plus 1 over alpha square root. So let's now look at this for the ground state system. You are going to do the n equal 1 quantum state. And I'll give you some guidance on that. But for the ground state, this is going to be equal to the normalization constant for the ground state is here. It's a square root of alpha over pi. So it's 2 times the square root of alpha over pi. Then we have the integral from, now for the ground state, it's 1 over alpha square root to infinity of e to the minus alpha x squared dx. That is the ground state wave function. So we need to simply do that integral. From there, I will guide you to the helpful handy-dandy integral wave function, or handy integral table. So here's our function right here. So we have e to the alpha x squared, where b is our alpha. So our answer to this is 2 times the square root of alpha over pi times this integral here, which is 1/2 square root of pi over b, which in this case is alpha. But we have to use this right here. We're not doing 0 to infinity. We're going from a lower limit, c, to infinity. So we get an error function complement. So this becomes ERFC from c, which is our lower limit, 1 over alpha square root, times the square root of b, which is the square root of alpha. So everything goes away, so it becomes ERFC of simply 1. So everything drops. That the error function complement of 1 is at 0.157. So there's the probability of of any vibrational system, because this is in general. I didn't do this for HCl or anything. But in general, if a vibrator is in its ground state, it has about 15.7% probability of being outside or inside of the classical turning points. And so that ends up being then a significant amount that allows for, like I said, proton transfer and a lot of other things. For your problem, I had you have a hydrogen molecule. I'd given you H2, and I asked you in A, what's the probability that H2 will be found in a classically forbidden region of space if the oscillator is in the n=1 quantum state? To do that problem, you need this integral here, and I've given it to you in the notes, okay? Because once you put it together like I did here, you're going to put the n=1 quantum state in place. When you do the probability, you will end up at this integral. And it involved a little bit of a transformation. I had to do a integration by parts to get there. I didn't ask you to do it, I just gave it to you here. So here it is. That's what you're going to need. So what's the probability of that H to be found in a classically forbidden region? You'll take twice the psi star psi, going from now A being equal to, now your n=1, so it's going to be the square root of 3 over alpha to infinity for your problem. When you put the n=1 quantum wave function in place, you'll end up with this integral, and so you'll be able to kind of solve it directly to get a numerical answer.
So for n=2, if n was to equal to 2, you're getting like 5 over alpha?
That's correct. So it's 1 over alpha, 3 over alpha, 5, 7, 9, so it goes in those odd numbers in there. So that'll ask you to do that. And then in part B, I said, what's the fraction of the root mean squared distance of the oscillator from that to the equilibrium bond? That I'm just having you redo this right here. So this is for chlorine, I did it for HCl, I did it for Cl2. So you'll do the root mean square distance there as well. So find out what that number is for H2. H2 is it's a kind of a worst case scenario. So the lighter the particles get, or the atoms get, the more coupled the motions become, the more spread it comes to that. It turns out that way.
Wouldn't it be like the heavier it is, also it's harder to see the vibration?
Yeah, heavier it is, the better.
The better. What if it's just like this?
Well, then it becomes classical.
All right.
Then it does not. It doesn't tunnel at all. That's right. So in B, so what's the fraction? So you're going to redo that problem. So all you will need, I've given you enough information to calculate the force constant and the reduced mass. So I've given you the vibrational frequency and the equilibrium bond distance. So find this as RMS to RE ratio for that. And then repeat that for deuterium D2 and tritium T2. Now the only difference between deuterium and tritium is the reduced mass. The force constant does not change. The force constant is dependent upon the electrons, not the nuclei. So we'll find that later when we do molecules. So the K will still be this value. The vibrational frequency does not change, but the mu, well, the fundamental does not change, but the mu will change, and that will change this. So the mu changes, the K put in the frequency for, since the K depends on the reduced mass, you'll have that change as well. So I just want you, when you go from H2 to D2 to T2, you just kind of get a general feeling of the tunneling probability. As it gets heavier and heavier and heavier, you should see the tunneling go down, down, down. So you will demonstrate that in C. And then the anharmonicity constant we have yet to deal with. So let's take care of that. So we have a significant tunneling. Now, going back up to our graphic, where I had this system right here, we are down in the lower vibrational state, which is super. But when we do spectroscopy, which we'll see next week, we'll be kicking things up into here, we're going to want some sort of a correction to the Hooke's law model. Well, if you go back and use this potential here instead of the Hooke's law potential here and do the quantum mechanics again, you have to do another series solution, but you come up with an energy correction. This is what we need for next Tuesday. So I talk about what about the energy corrections for, so there's our tunneling here, come back down here. All right, now, so going back and now using a Morse potential rather than a Hooke's law potential, we get an energy that has a harmonic term, and subtracted from that, we get what is an anharmonic term. So here's an energy correction for that deviation from the harmonic model. And I draw both of these, and when you get that, you get an interesting result. For the Hooke's law model, there's the potential energy here. The energy levels are evenly spaced. So you get boom, n equals 0, n equals 1, 2, 3, 4, 5, 6, 7, and so forth. If you incorporate a Morse potential, you get an interesting result. Now this one then expands, it doesn't continue to rise, it accelerates here more rapidly, and the energy levels start to get closer and closer and closer together. So as you come up into here, the energy spacings become small enough that when they turn to 0, the molecule then dissociates because there's no energy difference between the two. So they do get closer together. When you look at that, you find when you do a delta E, well then, now delta E is the energy difference between one quantum level to the next. For the harmonic model, the energy spacing from one level to the next is constant at its vibrational frequency. For the Morse model, the energy spacing is its fundamental vibrational frequency or wave number minus a 2 times n plus 1, the quantum number, times what is called the anharmonicity constant. This is a value that can be determined spectroscopically. We will do that next week when we meet over that. But when this value turns to 0, the molecule then breaks apart. So this will tell you the maximum quantum number that you can have for a molecule before it dissociates into atoms. And in doing so, if I set this equal to 0 and solve for the quantum number for HCl, HCl is a fundamental wave number of 2989.7. I multiply by the speed of light to get the I could if I got the frequency. The anharmonicity constant for HCl is 52.05. Again, we will find that spectroscopically. But if I solve this for the quantum number, it gives me a maximum of about 27.72. So what that says is the maximum quantum number that HCl can have is 27. If it jumps to 28, it becomes atoms. It becomes hydrogen atoms and chlorine atoms. So remember that we have to have quantized states. So the Nmax from this is about 27.72. So for promotion to n equal 28 will result in dissociation. So we'll find that. And you're going to do that for iodine, like I say, next week. We'll get that from the spectrum. I can connect the two by doing a series expansion. And if I do, well, we can find out that the connection between the Morse parameters, like the Morse potential, if I draw, let me pull that up here again. Remember the Morse potential, where is that? It looks like this. Here's the potential for the harmonic oscillator model. The Morse model is a dissociation energy, and 1 minus e to a beta factor. X, again, is the dissociation from equilibrium. We do that squared. I can connect the force constant from the harmonic model to the other parameters from the Morse model by doing a series expansion, and you find out that if you want to, or if you have one, if I have the dissociation energy for a molecule and its frequency factor, I can compute the force constant. And if I compute the force constant for the Morse potential, I get a value for that of about 520. The measured value is about 516, so we get less than 1% error on that. So the Morse model works actually quite well. All right, so we can connect it to do an anharmonic system, which we will need if we promote molecules to excited states. The last thing that we do, just like we did with rotation, is say, what do we do about polyatomic particles? Well, here we have a little bit of a problem because we have force constants that are really different. So right here, this is the force constant in the x direction for particle 1 based on the movement of particle 1, 2, and 3. So it's given as a kxx, a kxy, and a kxe, where it's read as k, for example, yx, is the force constant providing the restoring force on atom 1 relative to the position of atom 1, that's the 1, 1, in the y direction from movement in the x direction. So in other words, atom 1 moves in the x direction, but because a spring is in kind of a diagonal, it's going to be pulled in the y direction. So we have that. Now that's only for particle 1. If I do this for particles 1, 2, and 3, we produce then something that looks more like this. So here would be the restoring force for atom 1 based on the movement for not only atom 1, but atoms 2 and atoms 3. So we get a 1, 2, 3, 4, 5, 6, 7, 8, 9 terms, and we're going to have 9 of those for x, f of x, y, and z. So we're going to have a 9 by 9 matrix. So 9 times 9 are 81 force constants. That's not really an acceptable problem. So the solution to that is almost identical to the solutions that we had when we had internal motions and center of mass motions. We pick a coordinate system. The coordinate system that is chosen is it's similar to a center of mass, but it's a vibrational center coordinate system. And when a coordinate system is chosen properly, you get a potential energy that depends on what are our motions of Q1, Q2, and in this case, a small delta. Those are what we have called before the fundamental vibrational frequencies. So for a three-dimensional molecule like water, water has 3 vibrations when you put it in the correct coordinate system. It has a bend motion, so it kind of bends in this way. Water also has a stretch, which is called a symmetrical stretch, where everything kind of stretches in that way. And then finally, water has an asymmetrical stretch, where one hydrogen goes this way, the water goes to the left, and the other one goes down. In any sort of chaotic motion that you can imagine vibrationally, they can always be broken down into these 3 fundamentals. Think about a particle moving like a moth flying around the room. And if you've seen a moth fly, you know they're all over the place, right? Any motion that you can imagine moving around the room can always be broken down into an X, Y, and Z motion. And you can combine. In a similar way, no matter how chaotic a vibration might be, it can always be broken down into, at least for water, these 3 motions. These are why these are called the fundamentals, and the fundamentals result in what you see in an infrared spectrum. When you see the major peaks, they represent these motions.
Does symmetry play a role in this as well? Because what if you have like deuterium?
Oh, absolutely it plays a role. Yeah, if this is asymmetrical, is HO deuterium, for example, then the motions are the same because that's just geometry. However, the frequency factors will change, and the force constants will. But those 3 motions result in not 81 force constants, but only 3. There'll be one for symmetry, there's one for an asymmetrical stretch, and one for a bend. And fortunately, then all of the Hamiltonians then are separable into, so the Hamiltonian for a symmetrical stretch would be a reduced mass for a 3 body. Here's the momentum squared, p squared over 2 times the reduced mass, and there's the potential of the asymmetric 1/2 k q1 squared, which is the symmetric stretch. Then you have an asymmetric stretch, and then in the bend. And since all of those Hamiltonians are now separable, we end up with the identical results as far as the energies go. So quantum mechanically, the energy, just like a diatomic molecule, is still n plus a half Planck's constant times the frequency of the symmetric vibrational stretch. So everything comes back together, so all the answers that we had produced for a diatomic molecule become identical for a polyatomic molecule, only if we know those particular, and that goes to their symmetry points. You may have, and anybody had inorganic yet? Maybe you've done symmetry elements. It goes to those. From the symmetry elements, you can deduce the motions, and from spectra, you can produce the force constants, and then you can put it all together.
How are the calculations the same if they're asymmetrical?
The asymmetry will still be separable.
Oh, okay.
They will still separate because that's simply a mathematical problem. And so the masses don't. The only thing that will change are the frequencies and the reduced masses. Because the reduced masses will depend on 3 different masses instead of a symmetric one. But it still applies the same way. So we always get then for any n number of atoms in a molecule, there will always be produced 3 translational motions, nx, ny, nz, 3 rotational motions, and 3n minus 6. Remember that one? Vibrational motions. So remember when we were doing the heat capacities, we had this 3/2 r, 3/2 r, and then 3n minus 6 for a non-linear polyatomic particle. And so when you do the math on this and break it down into this kind of a vibrational coordinate system, you will always get 3 3n minus 6 vibrational modes for a nonlinear molecule, and 3n minus 5 for a linear molecule. So there's, again, these are the water molecule asymmetric stretches in the bending mode. And to be a true vibration, just as in rotation, the center of mass of the molecule cannot move. For a genuine rotation, the particles, the atoms rotate around its center of mass. That is a true rotation. If the center of mass moves, that's translation that applies to the particle in the box problem. But in vibration, it goes in the very, very same way. The atoms may move, they may stretch and compress and do all that. The center of mass does not, just keeping that in play. So we could always then, for any polyatomic particle, we could always break it down into translational center of mass motion, rotational motion, and vibrational motion. This went to, I don't know if it's still in your Dropbox. When I did I had a worksheet that we didn't go through too much, where I just kind of did for the HCl molecule, and I presented a set of spatial coordinates and momentum coordinates. And I was able to break down the position and momentum. This was classical. You can do quantum mechanically as well. The space and momentum, I could always break it down into translational motion, rotation, and vibration. How much of the energy is partitioned in each way. So the fact that we can break these things apart gives us a great deal of information about where it is moving, how it is rotating, and how it is vibrating. So that was just a worksheet that, we didn't go through it. I was kind of I'm trying to reduce content a little bit, so not to overwhelm you, because PChem can be a touch overwhelming from time to time. So anyway, but if that's the point, is that being that we have a center of mass system, that we have a vibrational kind of center of mass style coordinate system, we can always take any kind of motion at any time of particle, break it down into fundamental vibrations, rotations, and center of mass motion. So now you know everything there is to know about motion. All we have yet to do, and this will be after this next exam, is to take all this information about translation, rotation, and vibration, find averages, build them up into quantum or Avogadro's numbers of particles to find all the thermodynamic values that we found and discussed last year. And now, instead of being empirical, we're going to have a fundamental theory to get us there. And you will be startled at how accurate the results can be. So you know everything there is to know about this. I have no more to tell you. This way in the literature. So when you look up anharmonicity constants, you'll see them as represented as nu chi. That's one number. That's not nu multiplied by another number. That's the number that I gave you in part D. And then I finally asked you, what's the maximum quantum number that H2 can possess before it dissociates? You will do this, and that's again for H2. Next week, you're gonna, once you get the spectra for iodine, you'll do it for iodine. And we'll talk about that next Tuesday. So we're all meeting here Tuesday for that. Everybody's gonna do that, it's an important one. I've said all they need to say.
Wait, are you done?
I'm done.
You know, you want more?
I know, and you know, I start with roughly. I'm leaving now.
You know, one more?